All right, it's a big day. Let's get started. So we're going to spend about half of our time in here going over a few things, and then we'll move over into the lab. Just to start, though, we're not going to have any class meeting on Thursday. Instead, the lecture recording is already posted online. So you can watch that at your leisure. But definitely watch it before Tuesday. We're having a quiz on Tuesday at the beginning of class. And odds are that something in that recorded lecture may show up in the quiz. Also coming up is, so there's a homework assignment due on Thursday. You should submit that before 3:30. It's just a normal standard submission time. And then the next homework assignment is going to be due the following Tuesday. This is one of those assignments that previously was a single assignment, but I split it into pieces just to kind of make it a little bit more digestible. I'm going to give you a handout back when we go into the lab, and it's some calculations related to measurements we'll take on the hydraulic jump. And so that lab demo 2, as it's referred to in the course schedule, should be submitted along with the homework assignment. Any questions related to the announcements? All right, so here's what we did last time. I know some of you were at the Virginia's conference, and hopefully you had a chance to review the video before class. Here's the Bellinger momentum equation, and what it does is describes the downstream depth after a hydraulic jump. And through a hydraulic jump, energy isn't conserved, but momentum is. Momentum is conserved. And so we can calculate the downstream depth using the momentum equation, and we can calculate how much energy is lost through the jump using this formula. And the book provides a graphical representation of the energy loss. This is just as a function of the initial energy that exists at 1. And you can tell from the curve of this that as the Froude number increases, the amount of energy loss increases, but the rate of increase is declining. So through a hydraulic jump, you can burn off up to about 85% of the initial energy that's available. What we're going to talk about before we go back into the lab is the location of hydraulic jumps. And you're actually going to see the hydraulic jump move back and forth depending on the slope of the channel. We can actually change the slope of the flume based on, there's like a wheel where we can raise or lower the upstream end. So consider this drawing of the hydraulic jump, and just like we're going to have in the lab, it's due to an underflow gate. So you have water coming from underneath a gate, and you'll notice that the opening of the gate is below the critical depth boundary line. So for any flow rate, you can calculate what the critical depth would be, and anytime the flow is at a depth less than the critical depth, and that means this is supercritical flow. But the supercritical flow can't be sustained indefinitely on a mild slope. And mild here has a specific technical meaning. It's not just like related to salsa spiciness. Mild here is referring to any slope that is less than the critical slope. And what do you think the opposite of a mild slope is? No, it's not spicy, it's steep. Less interesting, right? It would be better if it was called a spicy slope, but it's mild and steep. So here, this mild slope just means that we can't have supercritical flow indefinitely, and the only transition that can occur between supercritical flow and subcritical is the hydraulic jump. Now, this label is calling this the ideal case. And so you may be wondering, like, what's so ideal about this? Now, we have some new variable definitions we haven't seen before. And the new definitions, there's y1 and y prime 1. And in this instance, what the prime is meant to indicate is the sequent depth after a hydraulic jump. And so there's the before and the after. And the before and after both have the same amount of momentum, but they have different depths. Remember, we looked at several different momentum depth diagrams in class on Thursday. And so y prime 1 means the sequent of the upstream depth. And here what makes this the ideal case is that it's equal to the downstream depth that's based on the uniform flow conditions, the normal depth. So based on this slope, based on the channel geometry and the roughness and the flow rate, if you used Manning's equation, you could just calculate some normal depth. And that's the capacity of the channel downstream. So you can get a certain amount of flow through a hydraulic jump and usually a different amount of flow through a channel. But in this case, the ideal case, both of those curves are equal to each other. And so a rating curve is a way to graphically represent flow rate versus depth. And here is a rating curve just to show you an illustration. You have flow rate on the horizontal axis and the flow depth on the vertical axis. And what this is showing is that if you have the two curves on top of each other, that means that for a certain amount of water going through this channel, there's going to be a certain depth, and that just coincidentally also happens to be the depth that it would need to be for the hydraulic jump. Now, I think this will make more sense when I show you a non-ideal case, but keep it in the back of your mind that ideally the hydraulic jump is going to set up just immediately after the gate. So the water depth is contracting briefly, and this brief contraction is gradually varying flow. But then as soon as it finishes that contraction, it immediately jumps up to the sequent depth. Now, in a non-ideal case, we'll have a downstream depth. And so you can notice that between the two, this one, the hydraulic jump was close to the gate. This one, the hydraulic jump is further away from the gate. And the reason why it's further from the gate is that the slope was changed. If you have the same amount of flow rate, but you make the slope steeper, then this new depth, y2, doesn't have to be as deep. So you can accommodate the same flow rate through a channel with less depth. The velocity will be higher, but you don't have as much depth as you did before. And you can actually, if I toggle back and forth between these two slides, you'll notice that y2, as it's shown here, appears to be shallower than this y2 was, because this slope is relatively mild, and this, although it's still less than the critical slope, the slope is steeper. And so what that did is, as they increased the slope of the channel, that pushed the hydraulic jump downstream. Okay? The jump moved downstream. And the reason for that is if we pull up that rating curve, the tailwater rating curve is below the rating curve for the hydraulic jump. Now, I'll give you a moment to think about how to interpret these rating curves. So say for a certain flow rate, if you have that vertical line going upwards for a certain flow rate, what it means is that you don't need as much depth in the tailwater, which means the channel that's receiving the flow. The channel is maybe nice and wide, or it's relatively steep. So for whatever reason, the channel doesn't need much depth to accommodate a certain flow rate as compared to the jump. The jump needs more depth. And so what's happening here is there's a longer period of gradually varying flow where the depth is gradually increasing until this y prime 2 matches up with the downstream depth y2, and y2 you solve based on Manning's equation. So this is the non-ideal case. They're still showing what the ideal depth would have been here in this dashed line. This was the previous one that we had before. But these two depths are closer together. y2 and y prime 2 are relatively closer together because this had to run a while before it went through the hydraulic jump. So the jump is moving away from the gate, and that happened because we made the channel steeper. So let me ask you this. What happens if we make the channel less steep? It'll get closer. I like the way you think. You're right. And in fact, if we go to an extreme, we can actually make the the hydraulic jump get close enough to the gate that it actually drowns the hydraulic jump, where it's not visible anymore. The hydraulic jump is still there, but basically the tailwater is encroaching on the jump, and so it's submerged. So this is called an upstream jump, and if we look at it from the perspective of the tailwater rating curve, then the capacity of the jump is beneath the tailwater rating curve. So that's just saying for a certain flow rate, the tailwater needs a lot of depth to accommodate that flow rate. And so that large depth is moving the flow towards the gate until you can't actually even see the hydraulic jump any longer. So these drawings here of the capacity curves, you should be able to understand and describe these. You know, in the final exam in particular, there are going to be some short answer questions where I'll look for you to do more than just, you know, plug numbers into equations, but really demonstrate that you understand concepts by explaining things like figures such as this, and being able to explain why does the downstream jump set up, or why is there an upstream jump. Any questions about this? Good question. So you're thinking about the real-world applications of this, right? Well, the hydraulic jump that comes from a dam is usually when the water is going down a spillway. And so they can't really control the depth of the water in the same way that you can from an underflow gate like this. Underflow gates are used in canals, though, you know, like irrigation canals that are a lot more common out in the western United States than they are here. And so in irrigation canals, they'll have to be careful about hydraulic jumps because it can really scour the bottom of a channel. And we'll look at a couple of different types of hydraulic jumps today before we go back into the lab, because they have some scour patterns, and sometimes the hydraulic jump has turbulence vectors that are going down into the channel and can be a lot more erosive than stable jumps where the majority of the flow is going in the direction of the stream rather than downward into the soil. So here are some of those jump types. Now, the most boring kind of a hydraulic jump that you can, excuse me, you can barely even see that an undulator jump is setting up. It's where the Froude number is just barely greater than 1. And it mainly just looks like some ripples at the surface where there's a slight disturbance in the water. And in the case of an undulator jump like this, the upstream depth and the downstream depth are very close together. They may differ by just a couple of percent. Yes? Well, supercritical flow reaching into subcritical flow. So, like, why would the supercritical flow depth be so close to the subcritical depth? It depends on the feature that's upstream of this. It could have been that a gate is open most of the way. You know, like if we go back to this example, let's go to the original case. If I opened this gate more, then at location 1, the Froude number would be getting closer and closer to 1. Like right now, because it's closed most of the way, the Froude number is probably pretty high. Like this is, just by the appearance, the Froude number here is very high at location 1. But if we continued to open the gate more, then the Froude number would be decreasing, and we'd be getting closer and closer to the situation of an undulator jump. And so we can set up an undulator jump back in the lab today just by opening the gate more. There are other features besides underflow gate that can cause a hydraulic jump. A weak jump is slightly more interesting to look at. You can finally now see a distinct profile in the hydraulic jump. Froude numbers up to about 2.5. Oscillating jumps are difficult to measure, and they cause a lot of ripples, and it's hard to know when the jump is ending and when it's just ripples. And we'll struggle with this a little bit today because part of what we're going to be measuring back in the lab is how long is the hydraulic jump, not just what are the depths, but what's the overall length from the beginning to the end. In the case of an oscillating jump, it's difficult to distinguish the turbulence of the jump from the waves and the ripples that it sends downstream. And so to get away from that, hopefully what we'll be able to do is get it so that we have a stable jump, which means that at location 1, the upstream profile, we want the Froude number to be between 4.5 and 9. Now, we're kind of juggling something, though, because the way that we have a high Froude number at 1 is by pooling the water upstream of the jump. But the channel walls only go so high. And if we have the water go higher and higher and higher, then it can actually spill outside of the flume. And so, unfortunately, that's kind of what we have to do. We're going to be really close to the edge of the maximum amount of water we can put in the sidewalls of the flume to get a good stable jump. But remember earlier I told you to keep an eye on these scour patterns, because in the case of a stable jump, down here within the jump itself, close to the channel bottom, the velocity profile is mostly sideways. In contrast to strong or rough jumps where there's a lot more force that's going down and has the potential to, here in the oscillating jump, there's also vectors that are going downward towards the bottom of the channel. And that's partly what contributes to the waves in an oscillating jump. So we'll just look at, as we play around with the depth of the upstream gate, the ratio of the upstream and the downstream depths. By the way, does anybody who was here on Thursday, or anyone who paid special close attention to the video, remember what are the assumptions behind the Bellinger momentum equation? The one that should concern us the most? What's that? You're on the right track. So something about the bottom. The velocity profile. Yeah, so it's assuming that it's a frictionless surface. We know in reality that when we have water in contact with the channel bottom, we're going to have a velocity profile where the no-slip condition exists. The farther away we get from the bottom, the faster the velocity profile is going to be. But down here, very close to the surface, in reality, the water velocity is equal to 0. We actually saw a video that showed that. Remember the injecting the dye at the bottom, and then they had to stir it up with a little stirrer for that dye to actually move downstream. And so we believe in the no-slip condition, but unfortunately, the Bellinger momentum equation, just for numerical simplicity, assumes a uniform velocity profile. So it's assuming that the velocity at the bottom of the stream is exactly equal to the velocity at the top of the stream. Now, that's a deviation from reality, and that's going to contribute to some of the error that we see in the lab today. The downstream depth won't be exactly what the Bellinger momentum equation would predict it to be, especially because we're going to be dealing with relatively shallow depths where the influence of that surface, the shear forces that's applying to the left, is really going to be pronounced. If it had been deeper, then it wouldn't introduce so much error. But unfortunately, for a small demonstration scale flume, that assumption is going to cause us some trouble and will introduce some of the errors that we'll see today. All right, so jump length. That's the other thing I mentioned that we're going to take a look at is there's the length of the rollers. Here it's designated L sub r, where you'd actually see white caps and foam in a field implementation of a hydraulic jump. And then the length of the jump itself is defined as just how long until it kind of gets back to the normal depth that you'd expect to see based on uniform flow conditions. So from the beginning of the hydraulic jump to when it reestablishes normal depth. Now, one way of finding out the depth downstream is to use this nomograph where the Bureau of Reclamation has kind of provided some pre-solved solutions that are based on the Froude number. So you'd calculate the Froude number upstream before the hydraulic jump, and then you'd go over here, up, sideways off of the curve, and then on the vertical axis is the ratio of the length of the jump to the downstream depth, y2. So you'd have to calculate the downstream depth based on the Bellinger momentum equation, and then from that multiply the downstream depth by whatever factor you got off of the vertical axis, and that tells you how long the jump is going to be. And it's just an approximation. You know, these are all empirical equations that are subject to some pretty healthy variations when you actually observe it in the field. Just some rules of thumb. If you look at the ratio of the rollers to the overall jump length, they say that maybe the rollers are about 40% of the overall hydraulic jump. So remember that 40% when we are back in the lab today, because what looks like the hydraulic jump, we actually have to keep going a little bit further before it's reestablished the normal depth downstream. The other challenge with what we're going to be seeing in the lab today is it's not actually the normal depth that the hydraulic jump is going to be running up to meet, but we have to drop a little plate into the channel to cause pooling for the hydraulic jump to match up to. So besides the uniform flow assumption, the other problem that we're going to have with what the Bellinger momentum equation predicts is it's not uniform flow that's in the channel, and I'll show you more about that when we do get back into the lab. So that's the first method, Bureau of Reclamation. The Hager method is another one where it's a function based on the Froude number. Our textbook calls the third method, they just say another jump length equation. They don't even bother naming it. So that's what we'll call it. We'll call it another jump length equation. And so the A values are between 5 and 7. So just to get a refresher, first of all, on how to use the Bellinger momentum equation, let's try this example. This will be good practice for what we're going to go witness back in the lab here in a moment. Let's say that we have a channel that's 25 centimeters wide, and we have a velocity upstream of 5 meters per second. And the depth upstream of the jump is 10 centimeters. So find the downstream depth of the hydraulic jump using the Bellinger momentum equation. And then based on these three methods, the Bureau of Reclamation, the Hager, and another, find out what is the predicted jump length for these conditions. Good question. So what to use for A? In this case, let's just assume that A is in the midpoint. I think in my example I used 5.5 for A. So go with that. Assume 5.5 for A in the another equation. All right, so our first thing we have to do is just a little bit of basic channel geometry things, you know, finding the cross-sectional area that the flow is going through. If we know the width of the channel and the depth, that gives you the cross-sectional area. And we have the velocity, so Q equals VA. That's where we get the flow rate from and put that into the Froude number equation. So the Froude number is 5.05. Now, by the way, in some of the equations, it was talking about Froude number. FR is the variable for Froude number. Here it was FN. It also means Froude number. Depending on the source that you're using, sometimes there will be slightly different variable definitions here. So if we put it into the Bellinger momentum equation with our Froude number, then we get that downstream of that depth, downstream of the jump, the depth will be 6.66 meters. And that was compared to 0.1 meters upstream. So it's a pretty dramatic jump. And then the length of the jump, if we go back to the figure, so for 5, let's see. Okay, so in this figure, our Froude number is 5. You go up along the vertical, intersect the curve, and so if we go over it, the ratio of the two is about 6.1. The ratio of the length of the jump to the depth. And so here, what we're doing is we're saying the length of the jump is 6.1 times the depth. So the overall length of the jump should be about 4.06 meters. Now, according to these other approaches, it says that the jump length is going to be either 4.96 if we use the Hager, or as little as 3.1 if we use another. And so that's quite a range here, between 3 and 5 meters, depending on which of these empirical methods is right. So keep that in mind today that, visually it's hard to pinpoint where the jump ends, and that partly is reflected in these empirical methods. That these empirical methods are just based on lots of observations over the years out in the field, people looking at hydraulic jumps and trying to estimate how long they were, and then come up with equations that described that. And part of the inherent inaccuracy of those equations is just the difficulty out in the field of actually deciding when the jump is finished versus just ripples in the water that would always be there. Yes?
Does 10H stand for hyperbolic?
Yeah. Okay. A related thing to the jump length is that there are equations that describe the profile, or just the shape of the curve. So as a function of x, you could find out how deep the jump is at any certain location by using either the Hager method, or there's a figure in the book, anybody want to try pronouncing this? Bakhmetov? Well, hopefully he's not rolling around in his grave. I just murdered his name. All right, so what we're going to do is back into the lab, and I'll bring the handouts and some other stuff, and we will get started with the festivities.